Good afternoon, everyone. Time since Einstein. Good afternoon, I'm John Hockenberry. First of all, I want to thank Tracy and Brian for single-handedly, using by force of will, their powers to bring this event into being and to make it one of the hottest tickets in town. Sure, I can remember when I used to, on a Saturday afternoon, watch totally awesome videos and think about, time, well, But to turn it into an entertainment genre, that's certainly an achievement. It's great to be here. Physicists, kind of have a way, we love them, of course, of appropriating concepts. And, the idea of time since Einstein might suggest that time was invented by Einstein. We, of course, being regular members of the human race, know that this is not actually true. Time, I think, though, is a little bit like love. It's accessible to all of us. It is intuitively experienced by all of us in the same way, yet it retains its mystery at whatever level you weigh in on it. It is a mysterious force that we all can experience and share and talk about, and indeed we all do. So I wanted to begin with a contemporary of Einstein's, the poet Yeats, who, like a lot of poets, talks about time. Because, of course, one of the things we would love to do with time is telescope it, to maybe get out of the present moment and speak to the ages in some sense. And here's William Butler Yeats speaking to the ages in a time called When You Are Old, which anyone can relate to. When you are old and gray and full of sleep and nodding by the fire, take down this book, won't you, and slowly read and dream of the soft look your eyes had once and of their shadows deep. How many loved your moments of glad grace and loved your beauty with love false or true? But one man loved the pilgrim soul in you and loved the sorrows of your changing face. And bending down beside the glowing bars, murmur a little sadly how love fled and paced upon the mountains overhead and hid his face among a crowd of stars. Notion romantic. He's, of course, talking about how he botched a relationship and wants to sort of explain himself before he dies. And then you've got that crowd of stars there in the end. Here's a little more abstract notion of time I think that we can all relate to. A poem called Peace. Ah, that time could touch a form that could show what Homer's age bred to be a hero's wage. Were not all her life but storm, would not painters paint a form of such noble lines, I said. Such a delicate high head, all that sternness and charm, all that sweetness amid strength. Ah, but peace that comes at length came when time had touched her form. Whirls you around. The thoughts of time are both intuitive and inaccessible, remote and exotic, but yet we know what he's talking about in some sense. And then, of course, this, a classic, right? Anyone can relate to this. The Four Ages of Man, William Butler Yeats. He with body waged a fight, but body won, it walks upright. Then he struggled with the heart, innocence and peace depart. Then he struggled with the mind, his proud heart he left behind. Now his wars on God begin. At stroke of midnight, God shall win. Unfortunately, God wasn't available for today's presentation, but we do have 6 people who come, I like to think, as close as we could get here for the World Science Festival. Please welcome our panel out onto the stage. Joining us to talk about time since Einstein, David Albert, professor of philosophy at Columbia University, physician, philosopher. David Albert is world-renowned for his insights into philosophical questions about the nature of time, particularly the arrow of time, which we'll talk about a lot this evening. He's written extensively about the tension between our scientific picture of the nature of time and our common experience of it. David, welcome. Right there in the center, the only one without a tie because he's from Caltech. Theoretical physicist Sean Carroll's research focuses on the question of why time moves in only one direction, that arrow of time, and how that may be related to the early universe. He is a senior research associate at the California Institute of Technology and the author of Eternity to Here, forthcoming book on the arrow of time. Next, on the end there, our good friend George Ellis, Professor Emeritus of Applied Mathematics at the University of Cape Town. He also has the largest number of frequent flyer miles here at the festival. George Ellis, an award-winning cosmologist who investigates the physical foundations of the flow of time. He believes that the current idea in theoretical physics about the flow of time being an illusion fails to capture the nature of time at the quantum level, as well as at the macro-physical level. A professor emeritus of applied mathematics at the University of Cape Town, as I said, he is co-author with Stephen Hawking of The Large-Scale Structure of Space-Time. That's the other book by Stephen Hawking that you haven't read. Yes. We are thrilled to have Michael Heller with us, there center next to Sean, professor of philosophy, the Pontifical Academy of Theology, cosmologist and Catholic priest. Michael Heller explores the intersection of physics, philosophy, and theology in describing the nature of time, particularly whether it is a fundamental property of the universe. He's professor of philosophy at the Pontifical Academy of Theology in Krakow, Poland. Markopoulou-Kalamara is a theoretical physicist at the Perimeter Institute, right here. She is a leading young theoretical physicist working on developing models of space-time that account for the flow of time. She's on the faculty of the Perimeter Institute of Theoretical Physics and is an adjunct professor at the University of Waterloo. We're thrilled to have her. And finally, Sir Roger Penrose, renowned physicist, has made seminal contributions to our understanding of space and time in describing the initial conditions of the universe. He provided the foundation for studying the origins of the arrow of time. Along with Stephen Hawking, he published The Nature of Space and Time, a record of a debate between him and Professor Hawking. Penrose, Emeritus Rouse Ball Professor of Mathematics at the Mathematical Institute at the University of Oxford, is the author of The Emperor's New Mind and The Road to Reality. So, if I am your launch vehicle for this discussion, these individuals are absolutely the planets in their orbits. We don't shy away from quarks and Pooh mesons or hadrons and Higgs bosons. We like to see them, and all of these people will present those concepts to you. We love to work at a very high level in these presentations, and also to keep it accessible. You know, I'm here and can fire the retro rockets at any time. We begin with a video to set up Einstein, time since Einstein.
Shakespeare had written, of course, very famously that all the world's a stage, right? And that's really the kind of picture or metaphor that Newton has in mind throughout his greatest work, the Principia. The planets will move around, the comets will orbit the sun, the apples will fall, and all that happens, all that action takes place on a kind of perfectly rigid, unchanging stage. And that stage is then space and time for Newton. So Newton says very famously, space and time are each absolute. They flow without compromise. There's nothing that happens on that stage is going to affect the stage itself. They're not actors in the drama.
Newton's view of time is what I would call the everyday notion of time that we grow up with, that we become familiar with in our everyday lives. The notion that time is universal. It's the same for everyone, everywhere, no matter what they're doing, that it ticks away at a constant rate, and time is passing equally and exactly the same for everyone, no matter what they're doing. And all of our everyday experience points to this being the correct notion of time.
And we come to Einstein, and especially with his general theory of relativity, his theory of gravity, space and time, or their union into space-time, now has become an actor in the play. It's not sort of set off apart from the other things like the planets whizzing around or comets or apples. It's now part of that story, so that the other actors, say large masses like the sun, can actually have an impact that can affect the shape of space, the flow of time in its vicinity, and vice versa. So they become part of the kind of stage play, not set off. So Newton had said time and space were, first of all, separate from each other, and were sort of absolute, apart, distinct. And Einstein starts folding them into the kind of larger drama.
In Einstein's theory of gravity, time becomes personal. So the time that elapses for me is entirely personal to me. The time that elapses for anyone is entirely personal to them. And the way that time elapses, the way that time flows for an individual is completely dependent on where they are and what they're doing. So if all the world's a stage, then the structure of that stage is the structure of space-time, this entity that Einstein introduced.
So to begin then, Michael Heller, there's this Newtonian idea of time, and there's this Einsteinian notion of time, and we're going to get to some post-Einsteinian notions. But there are notions and ideas of time that precede even Newton. Catch us up to these more ancient notions of time and sketch out a little bit, if you could, that they're perhaps more similar than we might think to some of our current controversies.
We have heard just a moment ago that the Newtonian concept of time is natural in the same for everybody and everywhere. But it was not like that before Newton. There is a strong evidence that the original concept of time for humanity was a cyclic time, enforced on our imagination by the cyclic idea of the year and seasons. And it was Plato in antiquity, far antiquity, who, so to speak, formalized that idea. And he said that circular time is but a shadow of eternity. Eternity for him was inhabited by immutable ideas, like, for instance, mathematical objects, which never change, which do not live in time. Time cannot make any damage to the mathematical objects. And this is eternity, existence outside time, without time. And we live in the world of shadows. You probably remember that famous questions of St. Augustine: what did God before he created the world? And the answer was that he was preparing hell for those who asked this.
Ask the question. I see.
But in fact, if we read carefully 11th book of his Confessions, we see that questions over there, but St. Augustine comments that this is a stupid question, stupid answer for a very wise and important question. And he says, what did God before the world was created? He said, there was no before, because there was no time. Time was created together with the world. And God lives in eternity, means outside time. And let's notice that the Newtonian concept of time, the time flowing from minus infinity to plus infinity, also changed our views on eternity. For us now, in our imaginations, eternity is infinite time, which was not before Newton. It was not in the medieval tradition or even Greek tradition.
Well, it's fascinating to see that this idea of circular time evokes a beginningless concept of time, and yet the arrow of time, the sort of procession of time, like the procession of numbers and integers, which invades the Newtonian concept, requires a beginning and creates this anxiety about the beginning, hints of physical debates that would take place in our time. Fotini, the postulation there by Mr. Kaiser in the video, that somehow Einstein dragged time from the audience or backstage and cast time as a character in this narrative of reality and actually put the stage up there as well. If we can move way beyond Einstein for a moment, what sorts of stories, what's the playbook like for time and space in this post-Einsteinian notion of time as you're studying it on the quantum level?
Well, okay, so maybe let's see how to think about time first, because you can say about time is there or time, the universe is always there in eternity. But in some sense, you don't have to think of it that way. You can think of time in a very physical way. So at 5:30, this discussion will be over, right? And we'll walk out and say that it's in our past. Now, why? It's not because I look at my watch and it's 5:30, that means the discussion has happened because the watch says 5:30.
No, in fact, it's all about this little clock here that's ticking. In fact, that is your reality right there, actually. But yeah, so, yeah, but anyway, go ahead, please continue. Yeah.
Okay, I didn't realize that. I was going to say, before you clarified everything, that there's something very physical going on. So what happens is that what you just said, which was very deep, is now in my past and has shocked me because the sound from your vocal cords have reached my ears, and the photons that have bounced off your skin have reached my retina. So something has actually happened. And that's why you're in my past, or what you just said is in my past. So the notion of a past is a very physical thing. Now, if it's so, then it could also be different. So for example, you could be sitting here and I could be sitting, so you could be sitting there and I sit here, but your comment did not happen to me. And I can arrange for that easily since I'm a theoretical physicist. I put a black hole back there that is just big enough to suck all the photons that way. So then I don't hear you, you're not here, I walk out, and there was no discussion, which is a bit of a disappointment. So
Don't tell my kids about that, that possibility.
I wouldn't even know who you are, so it's okay.
Yeah, that's right. That's pretty complete. Roger, if we're going to talk about this idea of time during Einstein, or the time concept that Einstein presented to all of us, I think the best most lay people can do is have some vague understanding that, okay, fine, anti-aging creams and all the stuff that you can get at Duane Reade will help postpone aging for a while. But if you really want to do it, travel at the speed of light. And that's really going to slow down the aging process. Beyond that, I think people don't really get a sense of what relativity did to this changed notion of time vis-a-vis Newton. Help us.
Well, I think one of the troubles is that these effects are very, very tiny. I mean, as Faye Dowker was explaining on the video, time is in a sense personal, but then you might worry, why is it almost exactly the same for everybody? And the thing is, it only starts to make a difference either with very great speeds, which is what you're referring to, or with large gravitational fields when the space-time isn't flat and you have to worry about different kinds of effects. But in fact, you think about it, we're only traveling at the speed of light. If you travel very close to the speed of light to a distant star and back again, then according to special relativity, and I may say it's very well confirmed, this kind of idea in observations, the time, according to you, would not be past nearly, I mean, there would not be nearly as much time elapsed, according to you, as there would be in the people on Earth, that their clocks would have raced ahead of yours. And these effects, although they're very tiny because we don't travel at such speeds, are still measured in particles and that sort of thing. But I should make another point here, is that if I walk up to you or you wheel yourself up to me, and we wonder on the Andromeda Galaxy, what is the event simultaneous with our meeting each other? Now, because we're traveling at different speeds, what we consider to be the same event on the Andromeda Galaxy would differ by several weeks. So the effect is not necessarily only something which comes in with large speeds. It's all there with small speeds, but you have to consider very large distances before that would be relevant.
All right, now watch what's going to happen here. Part of my role here is to be the person that these formidable scientists on stage will be continually reminding, no, actually that's not quite right, John. In fact, you got it wrong here, bud. Perhaps in the occasional case, you know, John, that's complete nonsense. So it's okay if they say that, it's fine. And you just sort of go with it here. But I venture out into this territory now. Why is it that two observers on the Andromeda Galaxy would observe two events happening on this stage very, very differently? Help me out here.
No, it's not that they would see. You see, we have to, I mean, if I'm walking towards you, I have to think which way around it is, because it's confusing, you see. If I'm walking towards you, and then I try to consider what would I consider to be simultaneous event on the Andromeda Galaxy. And I would consider that event simultaneous with when we meet to be later because my time, you have to draw pictures, and I'm not allowed to draw pictures here, I have to do it.
Right. Okay.
But the time, because you have to think of it in terms of space-time, you see, and then you have to, I'll draw a diagram with my hands, you see. There's time going up this way and space this way.
Right.
And so as I'm walking along, you have to think of my world line, as it's called. That's, you see, as I walk, I trace out essentially a curve in the space. And that's got a slope to it. And the slope of that means that what I consider to be simultaneous with any particular event on my world line tips up by the same amount as my slope tips this way. And so what I consider to be simultaneous with our meeting is therefore much later on the Andromeda galaxy, supposing it's that way. I have no idea which way it is.
All right, so I roll towards you, call my friend
Yes.
on the Andromeda galaxy, and
Well,
say, I told you to be at the restaurant the moment I meet Roger Penrose. And the guy says, I'm not going to be there for a couple of weeks.
Exactly.
Why did you call me so early? That's the
Exactly, except that your signal, you see, has to travel with the speed of light. And that won't get there for weeks is nothing, you see.
Yeah.
But if you could send an instantaneous signal, yes, that would be right. And the sort of contradictions you get there arise because you can't send. I mean, that's part of Einstein's theory. You're not allowed to send signals instantaneously. It has to be delayed by the speed of light. So I'm afraid you can't send your signal and tell them.
I can't confirm it, but it's a great thing to think.
By the time they get your message, they'd be long dead, I'm afraid.
Right, I'd be like, yeah, it's the story of my life, babe. Yeah. So David, how internalized do you think, and you know, whether we're talking about your students at Columbia or just the sense of this debate in the way that we understand it in contemporary culture, how internalized is this notion of Einsteinian relativistic time, do you think, in the language of science as non-scientists maybe understand it? Is it working in? Professor Heller described a situation where, long ago, a circular notion of time was intuitive. We're reaching the point now where I think a relativistic notion of time is actually slipping into the vernacular.
I certainly think that's true of the language, but I think what Professor Penrose just pointed out about the remoteness of these relativistic notions from our everyday experience, because we're limited to slow speeds, because we can't survey vast spatial distances quickly. It's going to remain remote, I think, from the everyday phenomenological experience of time as we encounter it in our lives, except if eventually, certainly technologically possible, that techniques of space travel, for example, could be developed such that the story that Dr. Penrose is talking about, called the twin paradox, might be something realizable at a certain point. That is, we might send twin brothers away and have them come back and find that the one that traveled is much younger than the one that stayed on Earth. And I suppose if things got to that point, these relativistic notions would become a much more integral part of the way we experience time on a day-to-day level. But I think...
But just to be clear, I have two sets of twins. You say special relativity does not need to clarify that point by actually sending twins up. There is enough actual experimental data to conclude that will absolutely happen.
There's no question about that. But it happens in circumstances that now, insofar as our culture is concerned, count as fairly exotic. Mm-hmm. It happens in particle accelerators, or it happens to minute degrees to things very sensitive, time measurement devices like atomic clocks, even if you just put them on jet planes or something like that.
Those are measurable effects.
That's right. Those are measurable effects, but they're very, very small ones.
And exotic, but still much more accessible today than at the time of Einstein.
Absolutely.
Sean, your students coming to these concepts, and even in your own work, we have the capacity to go well beyond Einstein in thinking about these notions of time right now.
Well, we are. In fact, it's becoming necessary. There were sort of two ideas, big ideas alluded to in the video. One, what we've just been talking about, the fact that time is personal in Einstein's universe, because what exists is not really time and space separately, but space-time. And time and space are different ways of slicing that up that might depend on your point of view. But then there's another idea, which is that space-time is itself dynamical, that it becomes a player, not just the stage. And that has dramatic implications for what Michael alluded to, the question of how long does time go? Is it eternal? Is it cyclic? Does it go in a circle? Or does it begin? Once Einstein comes along and says that space and time respond to matter and energy, then Lemaitre, a Catholic priest, puts it all together and says, well, we have stuff in the universe and it's expanding. If I wind the clock backwards, it came from a moment in time which we call the Big Bang. And then scientists have gotten used to the idea that when people ask us what happened before the Big Bang, we give St. Augustine's answer. We say there was no such thing as before the Big Bang. So a new possibility opens up that really there was only so much time in the past universe, 14 billion years. But in very recent times, you're asking how we move beyond Einstein, increasingly we're realizing that this little bit of conventional wisdom that we hand out that says that there was nothing before the Big Bang, we have absolutely no justification for saying that that is true. General relativity says that something happens at that moment in the universe, but general relativity also says that general relativity is not right at that moment in the universe. We hit a singularity, the equations blow up, there's no reason to believe that Einstein's theory applies to that moment. We have to move beyond Einstein to understand what happened at the Big Bang. And the answer might be that the universe came into existence at the Big Bang. There was nothing before. There was the first time when we could talk about time. Or it might not. There could be something before the Big Bang. And in fact, what happened before the Big Bang could be crucially important to helping us understand why conditions near the Big Bang were what they are. So cosmologists, people like Fotini who are working on quantum gravity, and a lot of people are very much interested now in using what we've learned since Einstein to try to finally resolve some of these questions and go back and answer St. Augustine's question.
George, how important is the debate or the existence of a beginning of time to the debates in theoretical physics right now? Can you do physics today without having, being in the camp of there was a beginning of time or there wasn't a beginning of time?
Well, yeah. What happened there set the initial conditions for the universe, and there's a lot of debate about how that happened and what the initial conditions were. But once those initial conditions have been set, then the thing runs, and you don't have to worry about how it got to be there. Let's take a biologist. A biologist does not have to worry how it got to be that state. It just has to be what it is now, and he doesn't have to worry. If you're a nuclear physicist, you have to follow it back to a certain time, and you say, I don't worry about what went before. I think we can do it very pragmatically, depending. But if you're a quantum gravity person, like Fotini, then you've got to worry about what it was and how it happened at that time. So it depends what your branch of physics is.
But we yearn for a certain consistency in time. It is time, after all. We're not simply talking about time as like one particle. Time does have this sense of being a medium. It's important to know that there's something called now. Do you believe there's something called now?
Oh, absolutely. And there are many theoretical physicists who claim that the flow of time is an illusion, that space-time is this block space-time which is just sitting there. And I think that's a great mistake. I don't think that's forced on you by Einstein's equations, because what happens, as was being said, depends on the matter in the universe. And the matter's interacting, things take place, particles interact, radioactive things decay. That affects what happens in the curvature of space-time. And according to quantum physics, you don't know the outcome of those events until they happen. There's this total uncertainty, which is, it's not an uncertainty of knowledge, it's a total, it isn't determined what will happen until it happens. And that means you can think of an evolving block universe. We know what's happened in the past. There is a time which is the present when things are happening, and there's a time in the future which it's not yet determined. That's my view on it, which is not a very widely supported one, but in my view, that has to be the way it is if we're going to take quantum physics into account, where events take place that are unpredictable until the instant they happen, and living systems, the brain, when we act. And the moving finger writes and having writ moves on. Until you've written it, it hasn't happened. Once you've written it, it is fixed and it has happened. And the moment when it happens is completely different from any other event in time in your history. Now, the way that it relates between different people's histories is where the difficulty comes. But in my history, this moment as I'm talking is different from the past when it has happened and the future when it has not happened.
Well, you evoke this arrow of time, which we're going to talk about in a moment. But Roger, before we go to the next video, I've always had a bit of a problem. In terms of physics, the question of the past, the present, and the future are not as crucial and mind-blowing as they are for us, humble living organisms, where if you confuse them too much, it can have really harrowing consequences in day-to-day life and almost everything else. But if physics presumes that there is a future and a past and a present, and that they all exist in some sense, how is that not an utterly deterministic condition, where if the future exists, then it must all be figured out, and that there's no way to deviate or to have events that are non-deterministic in some way, that can be surprising, that have no preconditions, that can be absolutely the cause of what happened afterwards?
Well, I think this is one of the reasons Einstein took a very deterministic view when he, after relativity and so on, he certainly took this view of space-time being, well, this block universe idea. It's sort of out there as a whole, and in a certain sense, it's deterministic because you can't very well do anything to affect the future because it's there in a sense already.
Is that what you believe?
I think that's, I'm not an expert on what Einstein actually believed, but I believe that, my opinion is that that is what he believed, yes. And I think that there's...
But what do you believe is true?
Well, you see, I think once you try to, classical general relativity leads you to that kind of a picture, yes. But if you don't happen to believe classical general relativity is the whole story, and if you think that quantum ideas have to be combined with general relativity, as Fotini is certainly trying to do, and many others are trying to do, then the picture could be a bit different. It could be severely different. And it's certainly, I think, one of the great paradoxes of the way we look at time in modern physics is that time, well, even if you do quantum mechanics, time is sort of outside and flowing. It's not so different from classical, it's more like old-fashioned physics, like Newtonian physics, because the two ideas haven't come together yet. That is to say, relativity, in which time is not ticking away externally, and in quantum mechanics, or standard quantum mechanics, you treat it as an external clock. But if you want to bring these ideas together in some kind of quantum gravity, something radically new has got to happen.
Well, Fotini, let me put it to you then. If there is a future, physically speaking, do you believe that that means it's also determined and there's kind of no point in doing one thing or the other, that it's all been figured out? Can there be a non-deterministic future that actually exists independent of this flow of time?
Well, so this is, as was already said, this is the conflict between the two theories, general relativity and quantum theory, right? So in general relativity, yes, it is deterministic. You never have to choose anything. Everything is chosen for you.
Which is depressing. Right.
Or freeing. Depends.
Okay. All right.
But in quantum mechanics, that's not true, right? So
which is liberating or depressing?
Depends.
Okay.
But so if I were, so you could just try to put together the two theories really naively and see what comes out. So if you go back to my thought experiment with the black hole behind you,
right,
then the correct way to do that is to say the black hole was really made of matter. And just like an electron in the double slit experiment takes all possible paths, so it can be here and there while it does that. So then the black hole is behind you and is not behind you at the same time. So the photons get sucked that way and not. So you are in my past and not in my past, which is a very strange notion of time. So if this is the naive quantum gravity
so strange that
theory.
it's not even depressing. It's just...
Yes.
Yeah.
So actually, that's a theory.
Being sucked into the black hole deprives me of a particular place in time, as well as everything else it deprives me of.
Yes. So, but then I end up with a very weird notion of time. I don't even know that you can call that a time, right? So you're in my past and not in my past. which, I mean, would you call that a time? I don't know. But
depends on really, if we ever went to any restaurants or maybe went to the movies, or depends on how far it got, I suppose. That was a cheap shot. I'm sorry. I can't.
It was.
It was cheap. All right. Well, that's good. We're going to talk more about that because this idea of go ahead, Michael, and then we'll take the
I think that some clarification is needed now. We have a lot of physical theories. And every physical theory consists of certain mathematical structure with which we know very well what to do, how to compute some future effects and things like that. But with every physical theory, we associate some picture, some image of the world. Let's call this ontology for a given theory. And during this discussion, and also in our personal interest, we want to create a global ontology. We would like to know how the world is really, in reality. But physics provides us with a bunch of various theories, and some ontologies of the theories are not in agreement with other theories of that kind. For instance, in general relativity, in Einstein theory of relativity, special and general, the ontology says that there is one space-time block universe. In thermodynamics or in quantum physics, ontology is different, and it suggests that the time is evolving, it's a process. And I think that we should simply take into account this variety of ontologies, because our knowledge at the present moment is not final. And we know only some aspects of the world, and we try to compose out of these aspects some totality. And it's a very useful thing to do, but we must be aware of the fact that it's perhaps premature.
Well, I think the very fact that we have different ways of looking at time up here on this stage is an indication of just how exciting this entire debate and exploration actually is. Let's explore now the intuition about time, that there is an arrow flowing from the past to the present to the future that is very, very difficult to escape, whether we embrace relativity or get into some of the fabulous kind of cutting-edge physics that Fotini is investigating. This notion of past flowing into the present, flowing into the future, the so-called arrow of time, is very comforting, it's very intuitive. It's also a big problem for science. Let's listen to the video.
If Einstein's theory is right, if space-time is what is real, if it really is the correct way to think about reality, then there is no flow of time. Everything, past, present, and future, exists in a timeless way, and the passage of time is simply a trick of our minds.
Time is something which seems to progress. And according to physics, there's nothing like that. You have space and time. Space-time, it's out there as a thing altogether. And what is it that's evolving? What is it that's, how does time kind of progress? And it has to do with our experiences.
Take a movie of things behaving in the micro world. Take a picture of it all. And then run the movie backwards. That what you see in this backwards movie also obeys the laws of physics. And that's not true, of course, of the movies you see at a movie theater or life. If you run it backwards, it doesn't look right. In everyday experience and in the macroscopic world, the past and the future couldn't be more different. In the micro world, if you ran the movie backwards, you couldn't tell which is the backward one and which is the forward one. That's really strange.
It's as though it's out there, and past and future are all sort of laid out in front of us, which is the view that one has in standard relativity. However, there is this strange feeling that we have of time progressing, and there is a direction in which time progresses. The past somehow determines what the future is, if you like, and the past is fixed, and the future seems as though it's not yet fixed. I mean, are these things purely psychological, or is there something out there in the physical world which is different about the past and the future?
All right, so Professor Albert, how important is it that these be reconciled? scientifically speaking?
Oh, I think it's enormously important that we end up with some single, internally coherent vision of what's going on. But I guess, you know, I guess I'd like to take issue with what I sensed was the impression being presented in the video we just saw, that somehow the advent of relativity is what makes a lot of trouble for intuitive notions about time flowing. I guess, and maybe this is a good question for the other panelists, I don't understand a deep sense in which it was less problematic in the Newtonian case. It's been the approach of physics, at least from Newton onward, to do something that philosophers refer to as spatializing time, as taking time to be another parameter of the address of an event, and what one wants out of physics is a description of where the events occur in this space and spatio-temporal stage, and what their relations are, and what their causal connections are, and so on and so forth. But the problem, what's difficult to get one's head around about talking about the flow of time, you know, the sense in which this metaphor of time flowing falls apart in one's hands when one examines it closely doesn't have anything very deep to do, as far as I can see, with relativity. It's much more elementary than that. It's a much more of a logical problem than that. When you talk about something flowing or changing or evolving, what you mean is that the thing of interest has different values or takes on different configurations at different times, okay? That at 5 o'clock, it has a certain configuration. At 6 o'clock, it has another configuration. Under such circumstances, we speak of things changing or flowing or moving or something like that. The minute you apply this language to time, okay, you say at 5 o'clock, the time is different than at 6 o'clock. Either this is meaningless gibberish, or it's true by definition, okay? And it's been this that's the basic, that's what's deeply puzzling for physics in talk about times flowing. There are surprises.
Wait a second on that. Let me just hold on. Mm-hmm. Are you saying that the only difference between 5 o'clock and 6 o'clock is the position of the sun, or the only difference between the number 5 and the number 4 is the shape of the symbol?
No. You're at a different location. The thought is, the way physics has always dealt with this is that the difference between now and then is very similar to the difference between here and there, okay? These are different locations in a space that's
if
larger.
I'm here and it's different than there,
yes,
that's great.
Yes.
So I can go over there.
Right.
But then I can go back to here.
Yes.
Now I go to then.
No, but here's
and come back to now.
No, but here's what you can't do.
I'm stuck.
You can't go to the left while you're going to the right, okay?
That is true.
And that's not something that strikes us as mysterious or requiring scientific investigation. That's something that's very obviously true by definition.
Understood.
In the same way, you can't go backwards in time as you're going forwards in time, okay? When one says, I'm going to the right, if you unpack this statement a little, what you mean is, I'm getting further to the right as time goes forward, okay? If you say, I'm going towards the future, and unpack it in the same way, you're going to get, I'm going towards the future as I get further towards the future. Of course, that's true. How could that not be true?
All right.
And if when you say, I can't go backwards in time, what you mean is, I can't go backwards in time as time is going forwards. That's exactly like saying I can't go to the right while I'm going to the left.
Well, but you at least have to grant Einstein that he did profoundly pose the question: why is time going forward to begin with?
I mean, what Einstein did had very radical implications about what we mean by the present, especially about what we mean by the global present. There was a notion of a global present which made perfectly good sense in the Newtonian context and which fails to make sense in the Einsteinian context. What this has to do with deeper, more intuitive notions of times flowing I'm not sure I understand.
All right, Sean, why, whether Einstein posited it or not, does this issue of our perception of a flow of time and physics apparent, doesn't need this flow of time? Why do they have to be reconciled? Why are they urgent in any sense?
Well, we think that the universe makes sense, ultimately. I think this is what David was just getting at, that there must be a way of speaking about the world that is internally coherent and consistent and so forth. And Frank Wilczek in the video mentions that the laws of physics at the microscopic level that talk about atoms or even pulleys and planets if you're doing Newtonian mechanics, or if you're talking about the curvature of space-time if you were Einstein, all of the fundamental ideas we have about the laws of nature have the feature that we can run them forward or backward in time and it looks the same. There's no intrinsic difference between moving forward in time and moving backward. It's just like if you were floating out in outer space, there'd be no intrinsic difference between up, down, left, right, different directions of space. But even though if you were out in space, you could get mixed up about up versus down, you're never going to get mixed up about yesterday versus tomorrow. You have a feeling that you know the difference between the past and the future in a way that apparently the laws of physics don't. So if we think that we obey the laws of physics, there must be some way to reconcile our experience of the world, our feeling that time passes, with the fact that it's nowhere there in the equations of physics that says that the past is different from the future.
Well, we've had relativity for a while. We've had some of these philosophical contradictions posed for millennia. The world seems to be doing just fine. George Ellis, why is this reconciling of the two notions a significant scientific question? Why do we need to know one way or the other since things have been going on pretty well for a while?
The human mind and so on is a separate problem. Let's first look at physics. There's actually a fundamental problem in physics itself. It's at the microscopic level that what Sean said was right. It's time reversible. But macrophysics is not time reversible. The second law of thermodynamics is one of the most fundamental laws of physics. And it is still mysterious at a certain level why at this average scale you get this arrow of time and at the bottom level you don't. But Arthur Eddington had a wonderful phrase about this. He said you could mess around with physics as you like, but if you ever get a theory of physics in which the second law doesn't hold, you must hang your head in shame and go and think of another theory. So the arrow isn't time. It's nothing to do with consciousness. It's already in physics at the macroscopic level. It's fundamental to all of chemistry because of that. And so in a sense, the problem is already how does microphysics relate to macrophysics? You don't have to bring consciousness into this.
All right, Roger.
Can you explain what the arrow of time is and what entropy is and what the second law is?
Well, let's talk about the second law. I wanted Roger to explain the second law there. When he says, if you mess with the second law, you're in trouble, what's he talking about?
Well, it was almost on the video, but then it got cut off. And it's this issue of things getting more random, essentially, as time goes on. And there's this notion of entropy, which in colloquial terms means randomness.
Or death, if you're talking about aging.
What did you say?
Death, entropy, death.
I think
aging.
That's misleading.
Yeah, possibly.
Randomness. It's the things as time progresses, and let me use the word time there, things get more random. You can be more precise about that. But that's basically the second law of thermodynamics. This notion entropy, which is a measure of randomness, roughly speaking, is increasing as time goes on. Now, I think there's a bit of confusion in the two things here. I mean, one of them is the time reversal issue. And I think perhaps the video was slightly confusing there because the entropy issue was about to come in, and then suddenly it became the time reversal issue, which are different things.
Oh, we're going to get to the time reversal. We'll get to the next video actually explains this.
I mean, the thing is that time, the fact that time is not the same going forwards as backwards has to do with the second law of thermodynamics, as George very clearly pointed out. And that's a very fundamental law of physics. And it's hard to get around. I mean, it's something we certainly believe in. So that's a way of distinguishing the forward direction from the backward direction. But it's to do with the statistics of what's going on. You don't see it in the actions of individual particles. The laws are symmetrical in time there.
Just to say that, the laws of particles in physics do not require that there be asymmetry between forward and backward.
That's right. I mean, there are some funny ones which are asymmetrical, but it's not clear what the importance of that is in this discussion. But yes, essentially the laws of physics simply are the same one way in time as the other way in time. But yet, if you have very complicated objects which are built up of lots and lots of particles because of the statistical law of thermodynamics, which tells you that the randomness or the entropy increases as time goes on. That's not time symmetrical. But you have to sort of trace back where's the origin of that law, and that all ties in with cosmology. It has to do with what the Big Bang was like and so on. So it relates to the other issue of the beginning of the universe, if indeed it was the beginning of the universe, and what was special about that. And that's a very deep question.
All right, well, we're going to definitely get to that question. Fotini, is it conceivable that time, which we think of as this flowing, smooth progression of seconds or minutes or hours, is actually more like a quantum phenomenon where it can be put into packets, that there are packets of time and that they can be doled out at different rates, and that could explain maybe a different rate of time at the micro level?
I guess I would first separate into what might be two different notions of time. I don't know if they are, but it might be a good idea to separate them. One is time as change, something that has happened. And the other is time as the time dimension of a space-time. So a space-time geometry that we live in, the universe. And the space-time geometry is fairly smooth. We live in a very special, if you like, very nice, low-energy, smooth, fairly flat world. So yes, the second has to break down. High energies at the Big Bang, in a black hole, it has to be more exciting than our flat world. So if you like, the geometric time has to eventually break down. That whether time has changed goes away, I doubt it. I don't know. I mean, there are people who would say that time altogether goes away, but I would expect that you still have a notion of time has changed, but at some point, just the notion of a geometry doesn't exist anymore. Maybe the notion of space doesn't exist anymore. So you might have more primordial things that still change, and so you have a notion of time there, but it's not the geometric one.
Well, if there's anything that scientists get nervous about, it, particularly physicists and mathematicians, it's any notion of asymmetry. And Roger noted a moment ago that this progression towards entropy is one explanation of the progression of time. And the next video, I think, will make clear why that is natural in some sense, but also represents a real set of irreconcilable differences if you talk about the past versus the future. Let's roll the last video here.
Well, there are certain things which are different about the past and the future. One of them is fairly well understood. Roughly speaking, that things get more random as time goes on. So things are more organized and they get less and less organized as time goes on. I'd like to use an example of, say, a glass of wine perched on the edge of a table, and it falls off and the wine splashes into the carpet and the glass breaks and so on.
We know quite well that we could sit here for as long as we'd like, and we're not going to see the opposite happen, right? We're not going to see that film loop run backwards. We won't see the glass suddenly recombine and it hop right back onto the table. There seems to be an actual decidedness, an arrow. There's one direction in which time tends to flow.
And I think it's fair to say that the problem of the arrow of time has not yet been solved. It seems to be closely linked to having a real theory of the origin of the universe. There must have been some kind of a beginning, where beginning means if you follow things backward, there has to be at least be a point where our classical notion of time breaks down.
Einstein himself hated the notion of a start to time. He hated it. He wanted a universe that had no beginning in time. He thought that was sort of aesthetically or philosophically most pleasing. It also, for his mind, was good. It got away from discussions of religion. He didn't want anything that sounded like the story of Genesis.
People might say, well, God did it, you see, so that maybe there was a divine creation of the universe and that it was set off that way. Well, that's a point of view. It's not my point of view. My point of view is we have to look and try and develop our physical theories further to try and understand where that came from. And that's a difficult issue, as you might imagine.
And it's what we're grappling with right here. If you think that you've been cast in an episode of Nova and watching the videos and experiencing this, it's no accident. The producer of the videos is our producer of this event, Allison Snyder. So the videos are terrific. Thanks so much for those. All right, two great points. One about the sort of beginning notion, which we'll get to in a second. But Sean Carroll, what is it about the observable physical qualities of the universe, either at the macro scale or the micro scale, which determines how we experience time? Is there any?
Yeah, no, I think that's exactly the right question. I think that I'm a little bit more fundamentalist than even most scientists about this, that it's the second law of thermodynamics that just determines absolutely everything about all of the ways in which we experience the future to be somehow distinguishable from the past at a fundamental level. So I think that someone should actually say what the second law of thermodynamics is.
Please do. Please do.
We have this notion of entropy, the disorder in a system. If you have an egg, unbroken and pristine, it's very orderly. The entropy is very low. You can tell where the yolk is and where the white is and so forth. If you break the egg and you scramble it, everything gets mixed together, the entropy goes up. And the second law says that if you're in a closed system, if you're in something that is unaffected by the outside world, entropy will only ever go up. It will never decrease. And that kind of makes sense at an intuitive level. There are more ways to be high entropy and scrambled and random than orderly and pristine. It's easy to turn an egg into scrambled eggs or an omelet. It's hard to turn an omelet or scrambled eggs back into a pristine egg.
The French have tried.
Yes. But the point is, I think that this idea of entropy increasing is at the heart, either directly or indirectly, of all sorts of things, of why we remember the past but not the future.
But can I ask one question about that? I mean, that seems to be something that applies to matter, to things that have substance. Why would that apply to something as intangible as, or abstract, or non-mass as space or time? It seems to me there's matter and there's space-time. That's what I was taught. Why would a product of, or a feature of matter affect these other elements?
John, that is absolute nonsense.
There you go. What did I say?
The laws of physics don't care, matter versus non-matter. And I think this is, it's very interesting to look at the history of this discussion. In the late 19th century, Boltzmann and other of the sort of heroes of statistical mechanics were really very close to having a deep conversation about the origin of the universe. They were talking about, does the universe go on forever? How do we explain the arrow of time that they knew existed and they knew was a problem? Why was the entropy low in the early universe? What they didn't have was relativity. They didn't know that there was expanding universe. They didn't know about the curvature of space-time and so forth. I personally think that Boltzmann, had he really pushed it, could basically have predicted something like the Big Bang. Not that space itself was expanding, but that there had to be some moment in the early universe of exceptionally low entropy from which everything came. But he didn't. Instead, Einstein invented relativity, and that conversation sort of got killed off because then you thought that, aha, there was a beginning to the universe, and therefore we still don't know why it had a low entropy, but at least there was nothing before that. We can hide our ignorance of why the entropy was low early on in our ignorance about the Big Bang. But nevertheless, once Einstein says that, the distinction between matter and energy, as you say, and space and time becomes much less discernible because you have a bunch of fields that propagate according to equations. And I can call some of those fields the geometry of space and time, some of those fields electrons and photons and other particles, but they all obey the same basic structure. I can talk about the entropy of a gravitational field. Stephen Hawking very famously calculated the entropy of a black hole. And so we can talk about the entropy not just of stuff in space-time, but of the whole universe all at once. And we're still stuck with the problem that it was very small early on, that it's medium-sized now, that it's growing to the future. We live in a universe that is 14 billion years after the Big Bang, but one that will apparently stretch on infinitely many years into the future. That's a very interesting place to be. We're sort of infinitesimally close to the beginning of the universe if the Big Bang really is the beginning. So this understanding that space and time obey the same kinds of equations that matter and energy do affects how we think about the problem very, very deeply, but it's still the same kind of problem.
All right, I want to talk about the expansion question and what that means for the arrow of time in a moment, but Michael Heller, you had a...
Well, I would like to notice only that, in fact, we are discussing here three concepts, not only time, but time, dynamics, and probability. The relationship between time and dynamics is rather obvious. We have a dynamical system if we have a set of bodies which change under the influence of forces, and time goes into the definition of the concept of force and into the, It describes changes of these bodies, the configuration of the bodies. But if we go to quantum mechanics, we have also a dynamical system, but there are no bodies which change in time. There are probabilities which are changing with time. We have a deterministic evolution, but of probabilities. And those probabilities evolve in a deterministic way. And only when we make a measurement, then the system, so to speak, breaks down, and out of those probabilities, we have an outcome. Something happens, this and not the other ones. And the concept of time, it seems, is closely related to this evolution of probabilities. I think it's a very deep physical and also philosophical problem.
Professor Albert.
Just two things. One is to answer the question you asked Sean, but in a slightly different way. Even before
you did say it was nonsense, right?
even before you get to, this is a different way of saying it's nonsense. Even before you get to anything like general relativity, just unpack the questions you're asking about the difference between past and future. Why is it that I can decide where to put certain objects 10 minutes from now, but I can't do anything about the milk I spilled 10 minutes ago? Why is it that I can remember, that I have very certain direct epistemic access to questions about, what the milk looked like when it spilled yesterday, but I don't have the same kind of access to what it will look like when I spill it tomorrow? These are, in fact, questions about the distribution of matter in space and time. It may seem, when you put the question in the form, why is the future open and the past closed? Why can we remember the past but not the future? The grammar of the way those questions is put is tricking you into thinking that you're asking a question about time itself, as it were, rather than the way material bodies comport themselves. But you unpack it a little bit, you are in fact asking a question about the way material bodies comport themselves. So I don't think it's surprising that what we learn about the dynamics of the evolution of material bodies has a very deep impact on these big-sounding, sometimes awkwardly put questions. Why is the future open? Why is the past closed? So on and so forth.
How is that more sophisticated than saying the milk doesn't care who spilled it? It's just distributing itself. It's just distributing itself.
No, but there are really interesting differences about, here are some differences, aside from the second law of thermodynamics. Sean thinks they can easily be shown to follow from the second law of thermodynamics. It seems to me it's not quite that simple, but let's
now
table.
You're not.
Let's
not absolute nonsense.
Let's
absolute nonsense.
Let's table that. But the issue is things. We have, for example, it's a very different matter for us to try to know what a glob of milk was shaped like yesterday and what a glob of milk will be shaped like tomorrow. Okay? This is a very deep asymmetry between past and future. It's also the case that we walk around thinking that we have some kind of control over the arrangements of medium-sized, not too heavy material bodies a day from now. We can make up our mind to rearrange our bedroom tomorrow, and we can be fairly confident that we'll do it, whereas we have the very strong impression that there is nothing whatsoever that we can do by acting now about the way the furniture was arranged yesterday.
All right, so the procession of us going towards entropy, higher states of entropy, is a procession that is fixed. And the reason that we have no access to the spilled milk in the past is because we no longer have access to those energy states. Those have proceeded now to the present and into the future. These are different energy states. These are different snapshots of the universe. We're not able to go there for the very reason that entropy proceeds at this particular state. You're shaking your head wrong.
Yeah,
you can only say nonsense once.
No, I think I mean, the sense is there, but I think I would just phrase it in terms of why we have the impression that, and I think David was very careful in his book.
No, you're right, you're right.
I mean, if you find an egg splattered on the ground, okay, and then you ask yourself, what can I say about the future of the egg and the past of the egg? There's a big difference. The future of the egg, I don't know. Someone might clean it up. Someone might fall and slip on it. A dog might come and lap it up. There's many, many things that can happen because the entropy is increasing towards the future. There are many, many possibilities open.
But the domain of things that can happen from now on is different from the class of things that happened before.
Exactly, because we're assuming all along that we live in a universe that came from a lower entropy state, and therefore probably that was an unbroken egg 24 hours ago. And that fact that that's a paradigm for why we remember the past and not the future, because we can, given data now, right at this very moment, draw implications about what must have been the case at some time in the past in a way that we just can't do about the future.
Roger, is an expanding universe a necessary and sufficient condition for us to understand time in the way that we do, or are they unrelated?
It's certainly not a necessary or a sufficient condition. They're related, but they're not the answer. I mean, the fact that I think that sometimes people used to suggest that the reason the entropy is increasing is the universe is expanding and all that, but that's certainly not right. I mean, you can imagine a contracting universe, and normally that would increase in entropy. Things would get more, well, things would fall into black holes, basically, and black holes are the largest entropy that one can have, essentially. So, but there is a fundamental mystery, you see, which is not understood simply by the expansion. And this is perhaps reflected in the main observation that we have telling us that the Big Bang is there at all, which is in the cosmic microwave background. This is radiation coming at us from all directions, which is commonly described as the flash of the Big Bang. It's not quite right because it's something like 400,000 years after the Big Bang, but nevertheless, you're looking way back into the past and you see this radiation. Now, one of the most significant features of that radiation is that it looks thermal. That is to say, it looks like something with very high entropy. Now, that's all ridiculous, because you say, how could you look back at the Big Bang and see something which looks like maximum entropy? Because it should be very small entropy, as we've been hearing. And the thing is that it is small entropy, but for a different reason. It's small because it's very uniform. And this says that the gravitational degrees of freedom were hardly excited at all. So there's a big mystery there. If you like, it's two mysteries. One is, why was the Big Bang so special? And the other is, why was it so special in a very, very particular way? And that particular way is that gravitational degrees of freedom were somehow not excited. Everything else was thermalized, but gravity was aloof from all that activity and only later on came in.
Is that to say that there was nothing gravitational going on before the background radiation event?
Yes.
Yes. Right, and that's the mystery.
Yes, and that's, if you like, a mystery. It needs explaining. I mean, there are ways of looking at it which maybe give explanations, but this is the big puzzle which seems to me in need of an explanation, yes.
Fattini, is there a way for you to describe how time might behave in a quantum probabilistic way that Michael suggested here, that we could perhaps grasp how it would be different as an observer from what we experience as time now? The idea that there is some sort of flux to the idea of flows of time, passage of time, the difference between now and then, that we could understand in a quantum way.
To some extent, the problem is, could you have a very ordinary, if you like, notion of time while making everything else consistent? Can you have the usual notion of change now, later, while incorporating quantum theory and all the things that we were discussing before? So, for example, in what we're saying about the black hole being there, not there, and then my past being a superposition of pasts, that's what I get by using the theories we have. So what it would be nice to do is, if I could break the sequence I followed and end up with a single past that is an ordinary past, because then I know how to understand that, I know how to do quantum mechanics with that, I can understand a lot of things. So maybe you could say that in in the argument I gave you about the black hole and it being there and not there, and therefore ending up with a weird notion of time, maybe I did something wrong. So possibly what's going on now is that we cannot really unify general relativity and quantum mechanics because there's some assumption that does not hold. And the question is, which is that assumption? And you can try different things. So George basically mentioned, I mean, his guess is really quantum mechanics. So at some point, quantum mechanics brings in novelty because you will end up in this branch or the other branch of the history you could have. My guess would be that maybe the notion of space does not work. So if the notion of space does not work at a fundamental level, then I could not have said that the black hole is there and not there because the notion of there is not true. So that breaks the sequence. And then I could perhaps have a normal notion of time. Not that anybody knows how to do these things.
Right.
But maybe I can raise another thing of a set of issues that we do not understand. And they have a lot to do with these questions that were being discussed so far, which is, if you like, the subject of emergence. So when you have basically, the things that everybody has been talking about is at some point you have a collection of objects, and then they start behaving differently than the individual objects do. So when you have a large number of things, they seem to acquire novel properties that you did not have before. And that's not something that we actually understand. So that is the subject of emergence. And maybe nothing special happens, or maybe that's where novelty arises. So if you have, say, a river, it's made of molecules of water, and I understand how the molecules of water work. But at some level, I have a notion of a wave, and that's a novel notion. So how come from these objects something new comes? And if true novelty can arise when you have a collection of objects, then you can solve a lot of problems that came up before. But that I don't think that we understand. Emergence and novelty and how these things work and what this has to do, if it has to do anything with quantum mechanics. This is a whole set of issues that are very interesting but not understood.
Which gets us exactly to your point about why would gravity have emerged at a particular point after the Big Bang, and that why would it be such a mystery what went on before? I mean, in a sense, is part of the question there, George, do you need to know if time began when gravity began? Is it pointless to set up a scale of time as though gravity's on some schedule 400,000 years after the Big Bang? Gravity is born, and that this is just some sort of eccentricity on our part. How important is it to peg this notion of a beginning?
From a philosophical sense, it's incredibly important because, as was mentioned, that's if it did happen, that's when things began. Okay, and there wasn't a before. So in philosophical terms, it's incredibly important. A return from the practical physics viewpoint. Once it's happened, what is normally called the Big Bang is not actually the big that instant creation. We know what happened from fractions of a second after the Big Bang on. We know everything that happened after that. And you can just say there is going to be an uncertainty principle in cosmology, just as there's an uncertainty principle in microphysics. You can follow things back, and we are always going to be uncertain. We can make all sorts of sophisticated guesses, but we're always going to be uncertain at a certain point, because the physics is never going to be tied down in experiments. It's always going to be hypothetical physics, which may or may not be true.
And that half second, as small as it is in units of time, is extraordinarily mysterious and significant to all of these questions.
Yeah. But what I would like to just focus on, the uncertainty at the quantum level can get amplified to big scales. And I'd like to give you two examples. One is, supposing we knew everything about life on Earth 4 billion years ago, we couldn't predict life today for the following reason. Life has been affected by cosmic rays which have affected the DNA. The emission of a cosmic ray is a quantum process, and if you have that excited atom, you cannot predict when it will emit and in which direction it will emit. So if you knew everything about the universe 4 billion years ago, you couldn't predict that giraffes and people would exist today, because uncertain events have changed the evolutionary history of the Earth. And so the process is indeterministic. Now, so you might say, okay, does that happen on bigger scales? It's happened in the creation of galaxies. At the very, very early part of the universe, there were quantum fluctuations which created perturbations which grew into clusters of galaxies, stars, planets, and the Earth. You cannot predict, even in principle, that the Earth will exist if you knew everything about the Earth, everything about the universe at the start of the inflationary era, because these quantum fluctuations were unpredictable, even in principle.
I mean, maybe it's just me, but I find that just enormously affirming and optimistic. I just think that's just so great. We want to get your questions here, but I want to just ask one final question before we put it to the audience. We're going to bring the house lights up in a moment, and you can just raise your hands. I'll call on you, scream out your question. I'll repeat it back so you can all hear it, and we'll go that way. We'll have time for a few questions. Now, the idea that physicists maybe aren't so concerned about the arrow of time, or have dismissed this idea that time moves in one direction and it's not a big concern for them, is belied by one very important feature of physicists, at least in my experience. And it's a feature of physicists which does not seem to comport with the biographies of, say, philosophers and theologians. The anxiety about the arrow of time on the part of physicists, I think, can best be demonstrated by the fact that it is the case that most physicists do their most important work in their 20s. This would suggest that they're very concerned about the arrow of time. Theologians and philosophers, on the other hand, often do, and frequently, most likely, do their best work in their later years.
It's mathematicians that do their best work in their 20s. Physicists do it in their 30s.
Okay. Thanks for clarifying that.
And then they appear on panels.
Right. I mean, as entropy increases over time, if we think about time as a great medium for acquiring wisdom, Professor Heller, is it the case that time confers some generous gifts to those of us who wait?
I think that time itself is a very generous gift for us.
Indeed. All right, let's turn it over to you guys. All right, we'll raise the house lights. So get see some hands here, a little bit more. Okay, right here, to begin. Stand and shout.
So we'd like to. I'd like to hear sort of your ideas about the instant, about now, because we like to think of the instant, or some of us maybe want to think of the instant as static. You know, if we could freeze right now and take the configuration of all of our particles that exist right now, that the instant is static, and we use that in calculus all the time. You know, we let time approach zero. And yet quantum mechanics says that, you know, that there can be no static instant. And so how do we resolve that, and does it imply that time is discrete in a way?
All right, is time discrete? Can it be stopped? And can we define now in any sense? If we were to freeze the state of the universe, could we in any way specify what now is?
This question opens up one can go in lots of different directions. Let me just maybe touch on two. One thing is, quantum mechanics has come up peripherally a number of times in our discussion here so far, and it may be worth putting on the table that the ideas that have been expressed in the conversation so far about the relationship between quantum mechanics and the direction of time, how to put it, are ideas that have many competitors on the table right now. We know of a number of ways of making sense of the foundations of quantum mechanics now. We don't know at the end of the day which one of them is going to be correct, but we know a number of promising attempts at making sense of the foundations of quantum mechanics, and in particular of solving something called the measurement problem, which is the central problem at the foundations of quantum mechanics. And it's just worth putting on the table that many of these ideas, indeed if you wanted to total them up, most end up counting quantum mechanics as a completely time reversal symmetric theory. I'm thinking here of attempts to solve the measurement problem like Bohmian mechanics, like the many worlds interpretation of quantum mechanics, so on and so forth. As a matter of fact, all of these have fundamental equations of motion which are completely time reversal symmetric. They also don't have the feature that what the world is an evolution of probabilities. It's an evolution of physical objects, which one can trace out step by step. So that's one thing I just wanted to put on the table. Vis-a-vis the question you asked about the present, one other thing that maybe ought to be brought up here is that the big Einsteinian innovation of abolishing a global present, okay, is something which, precisely because of quantum mechanics, there is now some uncertainty as to whether we're going to be able to stick with that down the road or not. That is, all of the ways, except for the many worlds interpretation, that we know of for making sense of quantum mechanics require that there be non-locality in nature, require that there be circumstances where doing something here instantaneously has effects over there. In order to
without a physical connection.
Without a physical connection and without any time interval in between them.
Got it.
In order to make sense of this instantaneity, it looks like, or it looks as if there's a danger that one may require an absolute notion of simultaneity of exactly the kind that the special theory of relativity denied. So one of the things that's going on at the interface between quantum mechanics and relativity is the possibility that we may need to rethink these sorts of things, that, for example, the sort of picture of relativity that was dismissed early on in debates between Einstein and Lorentz at the beginning of the 20th century might need to be looked into again.
Sean, can you give us a sense of the many worlds explanation that David referred to there?
Well, the wonderful thing about quantum mechanics is that it says that a lot of things that you perceive about the world aren't actual direct apprehensions of what the world really is. That what you can possibly observe is much less than what really is. And so the classic example is the position of some particle or the position of a cat, for example. In quantum mechanics, it's not that we don't know what the position of the cat is, it's that there is no such thing as the position of the cat. There's something which we call a wave function or a quantum state, which is the answer to the question, if I were to look for the cat, where would I see it? I never see the wave function. I see individual locations of the cat, but reality is much richer than that. So the conventional way of understanding this measurement problem, this way of understanding what happens when we look at the cat, is that it goes from being a wave function with all sorts of possibilities to being, bang, it's right there, the cat, I saw it is there, and now its wave function says it is there. The many worlds interpretation says, in fact, what happens is that I have a wave function, the cat has a wave function, and the idea of the cat is a chance to be there and a chance to be there evolves into the cat is there and I saw it to be there, and the cat is there and I saw it there. So in fact, when I observe something, after that observation, there are two me's, there are two people. They might both not be me, but they have the same memories that I do, except that one of them sees the cat there and one of them sees the cat there. And this happens only one way in time in the real world. We don't unmeasure and uncollapse the wave function and unbranch different worlds. And that's a bit of a mystery, I think, without...
But the outcome of the probability is basically the event in time. That basically...
the outcome of the observation.
Right, the outcome of the observation. Okay.
That's right.
And the probability of it occurring one way or the other.
That's right, and I think ultimately it's going to be a common explanation between that fact and the fact that the early universe has a low entropy.
Just to elaborate on that for a moment, I mean, one can sort of take what both of these gentlemen have said and just mush it into a kind of a, well, time changes the more you pay attention to it. You pay less attention to it, it moves at one rate. You pay a lot of attention to it, it's shaped really differently. Is that what they're saying, or is it much more sophisticated than that?
I think...
What are you pointing at?
I will answer in the following way. We are discussing two conceptions of time. One, that the time is something very real, and I would call that arrow of time problem. And another one is that time is not real, and I would call that error of time problem.
Great. All right, more
Probably
questions.
both are erroneous.
Those are important problems. Yeah.
What?
Probably both are erroneous.
What? Say again?
Probably both are wrong.
Both are wrong, which is also reassuring. Right here. Stand up. Sean. How fast is the universe expanding, and how does that compare with the speed of light? Anyone want to take that one?
It's doubling in size every 10 billion years. But the problem is that that's not a speed, so you can't compare it to the speed of light.
George, you want to say something?
I think Roger wanted to say something first.
Go ahead.
I mean, I think the thing that people worry about is that it seems as though the universe is expanding faster than light, and one is supposed not to be able to travel faster than light. But the thing is that the limit on the light speed is a local thing. You can't travel with a speed greater than that of light, but the things that are a long way off, whether you consider them to be traveling faster than light or not depends on how you measure things and so on. And it's not a contradiction, that's all I'm saying. That the special relativity limit on the speed of light, that Einstein says you can't travel faster than light, is certainly not violated by the universe expanding what seems to be measured to be faster than light, because if you take the distance just in the way you were saying.
So at an instant, there is a sphere out there. The Hubble's law says the velocity of galaxies changes linearly with distance. That's exactly true in a surface of constant time, and there's a sphere there where they're receding from us at the speed of light, but that has no observable consequences.
All right.
If you were traveling out there, you would be going with it, you see.
You'd be going with it, so right, so you wouldn't notice. All right, let's see. I'll get someone from the back. There, young person. No, actually, right behind you. Right behind you. Yep, go. I'll get you. Don't worry. Yep. But it's just a function of how bad the light is. I assure you. Go ahead.
All right, I was glad to hear talk of non-locality. So I was going to ask a question about entanglement and its impact on time. Maybe what you would call nonsense, but isn't entanglement timeless? I guess to the degree you feel that we are entangled, the universe is entangled at a quantum level, and doesn't that also sort of refute the indeterministic argument, and it is deterministic? Does that make sense?
All right, a lot of concepts there. Entanglement, someone please explain what that's all about. We're entangled in time at a quantum level, and how does that relate to the notion of the universe being determinist or non-deterministic, please?
Good. First of all, on entanglement, it's an enormously interesting and unsettling feature of quantum mechanics that that a certain fantasy that had been operative in science up until the moment of quantum mechanics, the fantasy that if you were to give a description of every elementary piece of the world, those descriptions taken together would amount to a description of the totality of the world. You might call this an atomistic conception of the way the world is put together. This idea collapses with the advent of quantum mechanics. In quantum mechanics, one can have, for example, pairs of elementary particles such that the pair has features that don't follow even from a complete description of particle number 1 coupled with a complete description of particle number 2. There are features of how they're related to each other that can't be broken down to those more elementary features. In circumstances like that, we speak of those two particles as being entangled with one another. I'm not sure I understand what you're talking about in terms of entanglement and eternity or something like that. Entanglement is a certain definite physical state that material bodies can be in quantum mechanics. just as with other states that they can be in, we have a dynamics that we have a set of dynamical laws that tell us how entangled states evolve in time, how entangled states can be generated out of unentangled states, and how unentangled states can sometimes be generated out of entangled states. And it doesn't seem to me that they have any special relationship to issues of eternity or determinism, but they do have a special relationship to these problems that we were talking about a few minutes ago with special relativity. It's because of entanglement that this phenomenon of non-locality arises in quantum mechanics. It's between pairs of particles that have this entangled relation to one another that non-local phenomena arise in quantum mechanics. And non-local phenomena may require, in order to give a clear theoretical description of them, some notion of absolute simultaneity. And if that turns out to be true, there is a very serious question about where that leaves the special theory of relativity.
So for entanglement to occur, there must be simultaneity, or for us to observe
no,
it
that's
or
too
describe
strong.
That's too strong.
That's too strong, but what's closer to the truth is that we don't know and have trouble imagining a way of describing non-local effects that doesn't require an absolute simultaneity.
Got it. The young person who I dissed in front of everyone, please. Yes. Go ahead.
As I understand it, if the universe is expanding faster than light, then from a third person's point of view, it should be impossible to get closer to the center. Is that correct so far?
Wait a minute. Now, the third person is positioned outside of the universe?
Somehow, yes.
OK, so to a detached third-person observer in a universe which is expanding faster than the speed of light, it is impossible for that third person to get closer to the center.
It's impossible for someone within the universe to get closer towards the center.
OK, so from the third person observing on the outside, seeing somebody trying to get closer to the center, they would observe great difficulty on the part of that person in a universe expanding faster than the speed of light. True or false, Roger?
I'm not sure I understand the question.
All right, keep going, keep going.
Anyway, what I'm trying to find is that since with the universe expanding, right, presumably the objects in it are moving outwards because everything's expanding, right?
Mm-hmm.
So since the expansion is faster than light and you can't go faster than light, you can't get towards the center, right? Now,
wait. Well, does that, go ahead, Sean.
So I think that there's a lot of truth in what you say, but none of the words you're using are words that a physicist would use.
Now, why couldn't you have talked nicely like that to me? Yeah, anyway, go ahead.
I respect him.
Go ahead.
Work is...
Right.
So the one very, very important thing is that there's no such thing as the center to the expansion of the universe. We think of things that are expanding as having, a point that is stationary and everything else moving apart from it. But if you were on some very, very distant galaxy, just like we see that distant galaxy move away, well, they see us moving away just as fast. So it's really just, it's not even that the different galaxies are moving through space. It's better to think of it as space is coming into existence in between the galaxies. There's more and more space. So the individual galaxies are stationary, but the space in between them is growing, so everything has a greater distance as the universe ages with everything else. Now, it can be possible that if you pick two galaxies very, very far apart, the effective speed between them is greater than the speed of light. And what that means, the implication of that is that if you start on one, you're never, ever going to be able to travel to the other one as long as that condition keeps going.
I would say that the best bet for them to get together again would be for the universe to start contracting it in, and then they can do it. So.
Any last thoughts? What is time, Fatini? Or any other last thought? Any other last thought?
Change.
Change? Time is change.
Well, there's this nice...
So the static time does not exist. That was the first question.
Yeah.
There is not.
Augustine has been mentioned a couple of times
Yep.
here. It's Augustine who famously said, time is the thing that you know all about until somebody asks you what it is.
That's good. That's good. Sean, you want one?
I think we talked a lot about entropy and how there's this big puzzle of how the early universe has a very low entropy. Something we didn't talk about is my favorite answer to that is that our universe is part of a bigger ensemble of a multiverse. And so my take-home message is that the fact that you can turn an egg into an omelet but not an omelet into an egg is the best evidence we have that we live in a multiverse.
It's not a physical question. The physical question would be how to measure time.
And there's no other question?
It is a philosophical question, but if we discuss physics...
Hey, no, philosophy, look, in a philosophical sense, what would your answer to the question of what is time be?
Well, I would have to prepare a two-semester lecture.
That's a philosopher's answer. That's a philosopher's answer. Roger and George, you want to take us out?
Well,
you first,
I would
Roger?
say it's what clocks measure.
It's what
clocks
measure. Good.
And I don't
George?
like multi-universes. I'll just get that in since I've got a second.
Is the universe a clock?
Yeah. You take a vote.
I want to just briefly return to a question which wasn't answered, is time discrete? I want to return to something the other day I said about space. I said that if you look between my fingers, the question is how many points are there between there? And according to the one view of physics, there's a real line of numbers between there. There's not just an infinite number of points, there's an uncountable infinity of points between them. I don't believe that. I think it's got to be discrete. There must be a discrete number of points. The same thing happens. If I say 1, 2, how many points were there between there and there? Was there an uncountable infinity of points? I don't think so. I think there was a discrete number of time events, if you like, between that one and that one.
All right, and if that is the case, and if we could observe it in a sort of quantized way, we'd have a considerable way towards some of the answers to the questions we've discussed today. I'm going to take us out with Yeats here. Anybody want to go for another hour? Yes. People are crazy. Crazy people. Crazy World Science Festival audiences. I love it. We'll leave you with The Coming of Wisdom with Time by Yeats. Though leaves are many, the root is one. Through all the lying days of my youth, I swayed my leaves and flowers in the sun. Now I may wither into the truth. Thanks so much for you and the panel.